Hi everyone, Anton here. Welcome to the fourth part in this tutorial series on generative models in Grasshopper. The series is part of the Computational Design Basics course offered by the Digital Design Unit at the Technical University of Darmstadt. In the previous video we built the optioneering interface to preview and browse through designs, and in this video I'm going to show you a sample workflow how to select designs based on different metrics or based on how they look and save them for later reviewing internally in your office with your colleagues or with your clients, and for further preparation of drawings, renderings and so on. So let's get started. First we need to prepare the definition for this workflow. So let's quickly rearrange that. I forgot to graph these shadows here because they are coming in as a list, so we should graph them the same way we graphed the geometry. Okay, and we don't need to have the preview on, so I'm going to switch that off. Then let's set the cutoff area in the filter, in the pre-filter part of the definition, which is here. Let's set it to 300,000. And let's wait for all the options to calculate. Okay, that took around 3 minutes on my computer, and we have 3,800 options. We can use the combination of all the floor numbers for each of the 9 tubes, which comes in from here. And in this component we actually joined it into one text object. Let's preview what we have. And it gives us the height of each tube separated by dashes. So we can call this our genome, and we can use it later on to kind of save and reinstate the solutions, the design options that we liked. So I'm going to create a text component here and call this genome. And then let's move this aside and group it. So that is our genome. And what we want to do next is to make the rest of the definition dependent entirely on this variable. Let me tell you what I mean. Basically the 3D model generation of the towers need to be dependent on that. The way we display them also dependent on that, and so on. So here where we pre-filter, let's make that a bit more explicit and call that a genome. I'll connect it to the output of that genome making component, and let's see what comes in here. We're using the text objects in this one. Okay, so this had to recalculate all the 3,800 options again. So let's reduce the number. I'm gonna set the cutoff area, floor area at 400,000. That should give us way less options, and the definition will be more responsive once we start reconnecting that. Okay, so let's see what we have. Basically, we want to create in this part the genome, creating part of the definition, followed by the pre-filtering, then followed by the 3D model generation, then followed by the analysis, and then followed by the actual optioneering interface. So let's do just that. So the genome comes right after where we numerically define all the solutions. I'm gonna kick this panel out because it's taking actually time to display these values, which happens here. Here we define numerically all the solutions. We don't need these since we are already displaying them in the display matrix. And this would be our part of the definition where we define the options numerically. At the end we get the genome, numerical description of designs, and then like I said, all the 3D modeling stuff need to go after we have pre-filtered the genome and need to be dependent on the genome. So the genome comes in here. Let's pre-filter it based on the area, which means we need to calculate the area. Let's drop that group. So calculate the area first. Okay, so let's see what happens next. Here we are filtering the genomes based on the area. So let's make some space and call that This is a text object. These are the filtered genome. Okay, and we actually want to use them from then on. So what happens here is we are reconstructing from the text of the genome the individual tube floor numbers. And it says heights here, but these are the number of floors of each tube. And we should actually stop using that since we want everything to be dependent on the genome. Disable that. And then let's make some space here. So I'm going to take all this and move it. Okay, so our 3D model is being created here. This is the area which we still need to calculate based on the genome. And this is also part of the 3D model. We don't need that old NURBS based model generation. So let's bring that in here into the group. Okay. And this describes the building. Good. This is the pre-filter. Pre-filter. Like I said, we don't need that. We are actually going to duplicate the area calculating group here and run it again on these heights. So this is our area. It's dependent on the genome. So let's make it also explicit. This is the genome and everything depends on it. It gives us the heights, and here we calculate the area. Okay, and the pre-filtering, we don't need that, and the pre-filtering comes in between. So, genome definition, pre-filtering, 3D model generation, analysis, and let's see now if we need to improve something in the UI. What would be useful is to actually see the genome for each building next to it, so we can copy it later and reinstate it. So let's do just that. We are going to take the genome text objects and bring them all the way to the sorting, so we can sort them accordingly with everything else. Let's create one more slot here, flatten it and pass that. So the sorted genomes come out of G. Okay. And now we want to use them in the labels. The labels are all the way here. So I'm going to add one more line here, genome. And then we need to connect that, but actually we don't connect it here, we connect it here where we are filtering based on the sliders. So we need to do the same with the genome. We need to graph them, use the cal mask, the culling pattern to filter it. So that would be our genome. And it goes into the merge component that feeds the values for the labels. So let's simplify this input, pass the genomes. What's happening now? For some reason they're not being displayed. They are numbers. this is a number parameter, yes, and our genome is actually text. So let's use the generic data instead of that. Pass this here, pass this here, and I see that we should not connect them at the bottom, we should connect them at the top. So here, and remove this one. We can actually go and delete this input. Okay, so now if we see in the Rhino, we have the genome that describes the building with all the tube floor numbers. Then we have the area, the shadow area, the park shadow, and the neighboring shadow, like before. But we have the genome as well. And the other thing that we can do is actually get a panel here to also see the genomes that are filtered. Let's also display here below the optioneering interface how many solutions have we filtered out of how many total, and how many are being displayed, because our matrix sometimes has less slots than the total number of solutions to display. So that would be useful information for later on. And since we are talking about the matrix, actually I think it will be more intuitive if we reconfigure this a bit. So at the moment, if one sets these sliders at 1, actually we have 2 by 2. Why is that happening? It's because, let's preview this, it's because 1 by 1 is actually the number of cells that are in the grid, but the points are 1 here and 1 here, so they're always with 1 more than the number of cells. So instead of using the points, let's use the cells, and we can get the control polygon of these cells, which would give a 5 points for each cell, the starting, then this one, then this one, then this one, and then again the start to close it. And here are the 5 points for this one cell. And then we can get the list item, we can get the first point, and use that one instead of directly the points. So that already looks better. Add to group. Now if we set this to 2, so it's, let me stop this preview. So it's 2 by 1, 2 by 2, and yeah, then you know what you're actually getting by setting these sliders. How many solutions are being displayed? This comes in here, where we're finding the minimum between the total number of solutions and the total number of slots. So this is the number that holds the number of displayed designs. Then let's take that here. Then we need to find how many designs we have in total. This comes in from, we can get that from here. So let's take the length of a list length, flatten this, and we have 9 designs at the moment. So that would be total designs. Let's take that number as well over here together with the other one. And how many have we filtered out? This comes in from here. At the moment we're filtering nothing, but if I reduce the maximum neighbor overshadowing that's allowed, then only one design is left, and we can get this number by checking the length of the geometry here. So let's do another list length, flatten the tree to a list, and here we have one filtered design. And let's take that number also there. Okay, so now we want to create a label. Maybe these numbers, we should move them somewhere here. So now we want to create a label that displays these numbers of design. Let me bring in a panel. Okay, so we want to say something like filtered down to X from Y designs, and then Z number of designs are displayed. So we want to display this text here next to our optioneering interface. Let's take in a text tag. Let's use one of these here. And the location will be slightly down from the endpoint of the first line. So let's find that. That would be moving along the Y direction with, let's say, 15, 20 units. Let's start with 15, but since we want to move down, let's make that negative. So minus X. There you go. And we want to move with this vector. We want to move the endpoint. These are the endpoints of these axes, but these are all the endpoints moved now. And so we want this item, we want only the first one. So that's the location. Maybe there should be a bit more. And then the text would be something like that. Then the justification, let's go for top left. Here we go. So filter down to X number of designs from Y total and so on. So let's do that. We're gonna use the concatenate text, and let's copy this and reuse it. So filter down to, delete the rest. That's the first one. Comes in here. Afterwards we have the number. Let's connect. This is our new text now. Then let's copy and paste again from, delete the rest. So that's, we need to zoom in and add another couple of other slots here. So that's the next thing we connect to the concatenate. From these are the total designs. Okay, so this is the filter design. So filter down from total designs and how many are displayed. So let's do that. I need to zoom here. Designs, leave the new line character in there as well. Then this one, and we need one more. Are displayed. So that's the last one. Okay, we need a space here. There you go. Filter down to 1 from 9 designs, 1 are displayed. We don't need that anymore. And that whole thing is our info text. Okay, next let's tidy up a bit the optioneering UI part. So here this belongs to the group. Let's bring that in. This belongs to that other group actually. So this comes in here. Then this is the new value, so that belongs to the group. This we are not using anymore. Let's make some space. Let's color everything black. So swatch black. So that would be black. I'm actually gonna change that to top right. Yeah, there you go. And this one is black. What else is black? Something here. Yeah, this tag. Let's also stop the preview on all these points. And the one below here. and somewhere one is left here. Yeah. Preview off. Let's also display the axes in black. So these are the axes. Here we need a custom preview. And take that black color again. We don't need to see this anymore. And everything that is kind of dynamic, let's color it in another color. So the text here and the slider values plus the lines, let's color that in something like green or something like that. Okay, so this would be the curves from the solutions. So custom preview. So these are the curves. This is the new color. Let's preview this off. And as well use it in the sliders. And in the text, info text. Okay, that's fine, and there is one more thing left to do, but first let's reset the sliders. So we have a couple of options here. There we go. And what's left to do is to move the outlines of the neighboring plots together with the different design options, so we can more easily compare how the shadow relates to the outline of the plot. So let's do that. The plots of the park and of the neighbor are here. So I'm just going to copy them and link them to the originals and move them all the way here where we are copying stuff in the matrix. And now we need to copy them in the same way we are copying the buildings or the shadows. So this is where we copy the shadows. Let's take that and let's just connect this here. Preview on. Let's use this custom preview here. There we go. So one of them is there, and we can also copy the second one. Hold the shift and then graft the tree. Graft it into a tree, so they get copied, both of them. There we go. Now let's stop the layer in Rhino, and then let's take this, all of this, into the group with the display matrix. Here we are, and that's the black color belongs here. Yeah, to go. Okay, great. Now we are ready to select some designs. First, I'm going to enable more designs to be generated, which can be down here in the pre-filtering. At the moment we're filtering everything that is less than 400,000 square meters. We filter it out. So let's go for 300,000 and wait for it to calculate. Okay, it calculated. Let me hide this menu here and use our browsing interface now to see what we have. We have 3,833 options. All of them are currently still considered, and 6 only are displayed because our display matrix is with 6 slots. So let's find a couple of designs that fit different criteria. We'll start with the design that has the largest total floor area. So I'm going to come here to the sliders, which control the optioneering interface, and I'm going to slide. The first one controls the area. I'm going to slide it up to filter everything out except for the largest one. As expected, that's simply 9 tubes, 90 floors high. So now we want to save this, and the way to do that is to come to where we preview the genome, the filtered genomes. I'm going to right click here, switch off the draw paths and draw indices. So this is our genome that is currently being displayed, and I'm going to right click and say copy data only, and then in a new panel, which I will call selected designs, I'm going to paste that. And what's important is to, since we're going to collect 5 designs, what's important is to switch off the multi-line data. And if you see something like this second item here, which is empty, double click and then delete the enter. Okay, so this looks correct. Then let's find now the design that is the top performing design on both the park overshadowing and the neighbor overshadowing. So I'm going to reset my sliders again to show all designs, and then I'm gonna reduce the maximum slider on the neighbor shadow to somewhere about here. Basically, this is the design we want to get. So if I slide the maximum slider on the park overshadowing, those designs will immediately be removed and we're going to be left with one design again. So that's the design that is the best performing design in terms of both the park and the neighbor. So let's copy that into our selected designs. I'm going to come here again to where we're saving that. So this is the genome of that design. Right click, copy data only, and then paste the result here. So we have now 2 designs. Next, let's find a design that has the minimum overshadowing on the neighbor and the maximum flow area. I'm gonna come again here, reset my sliders, and we want to have the best performing design on the neighbor overshadowing. So I'm going to reduce the maximum. Let's leave it here. And then we want the maximum area that this one gives us. So it's going to be this one here. So I'm going to increase the minimum cutout, and there's the design. So this is best performing on the metric of overshadowing the neighbor, and at the same time of all these has the highest amount of floor area. So let's save that as well. Right click, copy data, double click, paste it. Okay, next let's do the same for the park overshadowing. Find a design that has the highest floor area metric but the minimum park overshadowing. Reset everything, squeeze this in, so the maximum cutout for the overshadowing. This should be okay. So one of these 2 points look quite good. So now let's increase the minimum cutout for the floor area until we're left with only 1. And as you see, this is the largest floor area that we can get with minimally disturbing the park. Let's save this design as well. Go back here, right click, copy data only, and paste it. Okay, now we have 4 designs. Let's find one more. Reset all the sliders. So for the 5th one, let's filter the least performing designs on the park overshadowing metric and on the neighbor overshadowing metric. So these ones here. Let's reduce the cutout like this and like this. And we are left with 168 designs. And then let's find the top performing ones in terms of floor area here. So I'm going to increase the minimum cutout. Now we have 7 designs, 6 are displayed, and let's just take a look what we have here, which one we like. So this process doesn't have to always be driven by the metrics. It can be also quite subjective. Use your architectural sense for shape, sense for the city environment around that building, sense for symmetry. I'm gonna go with this one, which looks a little bit similar to the typology of the Sears Tower, which has this intersecting squares, and it's quite symmetrical. So I'm gonna go with this one. How to single it out though? Now we have all these 6 designs, and if I go to the panel where the genomes are being displayed, I cannot know which one is it, which one is particularly this one. Maybe I can type this number manually. That's one option. The other option would be to actually bake it in Rhino, bake the labels in Rhino. The labels are here. Bake the labels, and then just copy it from here. So this is the design we want. Cancel, and I can undo the bake while in Rhino, and then paste in the genome string. It looks comes in white text, but if we press enter, and that would be formatted, and then we just need to get rid of this last empty line. Okay, so now we have 5 designs, and we want to display only those 5 designs. How can we do that next to each other? We can do that by taking these selected genomes and going at the front of our definition to the point from where on we made it dependent on the genome, which is right before the 3D model here. And instead of the filtered genomes based on area, we are going to pass, let's save the definition, we are going to pass this one. Only one is being displayed. That's because the sliders are not reset. If I reset them to the maximum and minimum respectively, here we have only the 5 designs we selected, reinstated by the genomes. And maybe we want to display them in a row of 5, not in 2 rows. So I'm going to come here to the display matrix, and in this I'm going to make 1, and this I'm going to make 5. There we are. And we are also sorting them based on the shadow they cast, each of these design casts, on the park. This is happening here. There is something red. So let's see why this one is red. What it says here is key and value list have different lengths, which means that one of these is not 5. We only have 5 designs at the moment. Let's check them. This has 5, this has 5, 5, 5, also 5, 5, 5, and 3800. So this one is not connected to the right component from where the genomes come. It should be connected, if we come here, it should be connected to this one. There we go. And they come in flattened here, so we need to graph that, because they come in grafted here. Let's make it like that. That would be selected genomes, graph this one, connected, and this is where we get our designs from. Let's see if that sorting thing is still red. No, that's now fine, so everything gets sorted. And we are displaying 5 options. They're also displayed on in the optioneering interface on how well they perform, but they have their design shape, their genome, and their metrics also displayed next to them. So let's make another layer and call it selected designs. Make it the current one, and let's bake things there. Let's bake these designs, which are here. So this will be the designs, shadow, shape, and the neighboring plots, and this will be the label. Right click, bake, and if I disable the preview in Grasshopper, here we have, in this layer we have 5 designs. Okay, so we used the optioneering interface to select 5 designs from the current design typology that we have in the parametric model at the front of our generative definition. But it's often the case that you want to test different types of towers, for example, in that case, different types of buildings quickly, and still connect them to the generative model, so you can explore more options for these designs. And this is a good time to talk a bit how generative design comes into your workflow. With generative design, it's very easy to fall into the trap thinking that you can create such a parametric model and feed it with parameters, with evaluating algorithms, so that at the end it spits out the perfect design for you. Unfortunately, if you do that, you're kind of giving up yourself voluntarily the benefit of your architectural design sense and intuition. But actually, true creativity is what we humans are better at than computers. So why give it up? Instead of thinking of generative design as building the perfect model that gives you the perfect design, I like to think of generative design as a series of iterations. You're building something, you're measuring and see how it performs, and then you're learning from that, and then you're building again. That way, you as an architect can use what you're good at, the design sense, your intuition, and the computers can do what they're good at, crunching numbers and calculating all these options for you to browse through. Then you can look at those options which will inform your architectural thinking so that you can adapt your model, adapt the way you analyze it, and learn more about the project you're currently working on. Throughout these iterations, you also involve your colleagues, your clients, and look at this project from different perspectives. And you can repeat that until you feel confident that you have unpacked all the quantitative and qualitative aspects of the design and move on to representing it in more detail. So if we think of our original task here, to create a tower with the maximum floor area at the same time not overshadowing the neighboring plots, with a given sun position, maybe the design we have is not the best one. So we might need to adapt that. What we will do next is create another tower design and feed that into the optioneering interface so we can see whether that's better answering our brief. So next we're going to create a quick parametric model of a different tower and connect it to the definition that we already have here, and select 5 designs for that other tower as well. So let's duplicate what we have here. I'm going to switch off the solver, select everything, copy paste, and move it down, and that would be the thing we disable. And let's call this part 4 alternative design. And then let's enable the solver. Okay, so that's still working with the 5 selected designs we have. Enable the preview, hide the layer in Rhino with the designs, and let's start building our alternative tower design. So the tower we are going to build next looks like this. It consists of 2 tubes. Let me disable one of them. So let's disable this one. So this is the one tube. At the bottom, the tube has 4 locations, 0, 1, 2 and 3. At the middle it also has 4 locations, but they are moving on this axis, not in a square, so left and right. And then at the top we've rotated the section 45 degrees to maximize the exposure to the sun, for example, and it also has 4 locations, 1, 2, 3, 4. The same goes for the second tube, so the 2 tube can move independently. So for each tube we have 3 sections, and each section can have 4 possible positions. In order to get a grasp of how many combinations that would result in, so that we don't let Grasshopper calculate 500,000 designs all of a sudden, which would take forever and crash the computer, you can calculate the combinations with the following formula. The number of states, in that case 4, to the power of the number of elements, in that case 6. So 4 to the power of 6 is 4096 combinations. In the example with the Sears Tower, we had 8 tubes, because the 9th was dependent on the highest of these 8, and each tube had 3 states. So 3 to the power of 8, that resulted in 6501 possible designs. So let's build this tower together. Like in the previous definition, we want to define the genome of all the possible designs here at the beginning. We won't be able to pre-filter based on area, because area would be difficult to calculate with these crooked tower shapes, so we're gonna use something else. Plus 4,000 options are not that many, the computer can handle it. So define genome first and then pass it to the 3D model generation. Basically that would be how we do it. And instead of calculating the area of the designs this time, let's use another metric. That could be the volume, which is way faster to calculate than contouring the towers. And the volume is still kind of relative to the area, so we could use that as a metric to define how big the useful space of that building is. Another metric we could use is to calculate the facade area, which in more complicated designs is actually important, since the facade area costs money. So sometimes you want to minimize that, maximize the volume. We are going to go with the volume in this case. So we'll start kind of backwards. We'll define the 3D model first and then do the genome definition. Okay, here is the 3D model part. Let me disable this one, so no designs are generated. And there you go. Why is there still a tower being built here? Let's disable this geometry. Or let's disable this geometry. There we go. So here we're going to build the tower. We are going to start with the 2x2 grid that's in the floor plan. And for that purposes, I'm going to get a square grid. Quickly configure it to half of the side of the building. The side of the building has the dimension of 3 times 23, so 69. Half of it is 34.5. Here we go. So this is the size of the grid. And we want a 2x2 grid. Let me zoom in here. And we want a 2x2 grid, so 2 by 2. So this is the floor plan. And then we want to select for tube 1 and for tube 2 one of these cells. So indices will be between 0 and 3 for the 4 items. So let's get in a slider and configure it to be between 0 and 3. Here we go. That would be for tube 1 and that would be for tube 2. Then we want to merge those, graph them so the 2 tubes stay separate, and graph also the output. The grafting on the input actually is important only once we have more options than one, but let's already do it now. And then with these indices we want to get a list item from the curves that are coming here. So those will be the profiles, curves. Those would be bottom sections. Flatten, so it's a list. That's the list. This is the index. And if I preview that, here we have moving the one tube, and here we have the second one. Okay, this was easy. Let's do the middle section. Those are 4 rectangles next to each other. We want them centered in this plot, so 2 on the left side of the center and 2 on the right side of the center, so to say. So what we need to do is to actually bring in the plot in our definition, the plot outline of the building. We have it here. I've drawn it in Rhino. So that would be tower plot. And let's find the center of it with the area component. Here we go. So this is the center point. Now we want to move this point 4 times in order to get the 4 points for the locations of the squares. 2 times we want to move it negative and 2 times positive. And the furthest away from the center we're going to go is half the size of the plot. So let's first calculate half the size of the plot. Division, this is the size of the plot, and half the size, so divide by 2. This is half the plot. So let's make series starting at that, but the negative of it, minus x. Here we are, minus 17.5. Then the step, we're going to have 4 items in this series, so let's bring that in. And then the step is going to be 1/3 of the plot. So let's take in this one and bring in a 3. the number 3, and this is the step. Let's see what we have. Minus 17.25, minus 5.75, then it goes to 5.75 and 17.25. So these are the 4 locations along the x-axis. So let's bring in the x unit vector, multiplied by that, and then let's move the center point, which is here, with these vectors. Okay, if we stop the preview of the area, now we have the 4 locations where the rectangles will be. But they are still in the ground, so let's move them up with, let's say, 150. We're going to move them along the x direction, so bring in the z vector and add the x vector and the z vector before we do the move. So here they are now 150 units up in the air, and we want to make 4 rectangles in these locations. So rectangle by plane, so that would require a plane. So let's do that a bit more explicitly. Let's take the xy plane here and use the center point as an origin for that plane. So this is the plane, and then let's move the planes actually. So here we have 4 planes now in the air, not 4 points, and use these planes for the rectangle. The reason I'm using planes already now is because in the next step, when we're doing the top sections, we want to rotate those. So it's easier to, point cannot be rotated. The plane can be. The size of the rectangle is this number here, 34.5 divided by 2. So, and we want to construct a domain for it, so let's do domain, and let's take in the number from here, and the same number again for the other one, and we're starting from minus. So expression minus x. So our domain is from minus 17.5 to 17.5 along x and along y. Here we are. So these are the curves. Let's take this over here and copy it. This would be the middle sections. Here we are, one of the curves and the other one. And let's do the same for the top ones. So I'm actually going to copy this part of the definition. We don't need these sizes, they would stay the same. The plane is fine, we're going to rotate it. This is actually going to stay the same. So let's reuse it. And then first of all, we want to move it to 400, let's say, 400. There it is. Maybe let's look at the top, what we have here. So now we want to rotate it diagonally, so it's oriented towards the sun, the current sun position. Let's imagine this is south. So we want to rotate this plane. Plane rotate. We want to rotate this plane with minus 45 degrees, and since all the rotating components require radians, we want to get the radians corresponding to these degrees. Here we are. So you see already rotated, and then we want to get the x vector in that plane, not the world x. In order to do that, we can come here and in plane find the deconstruct plane. Here's the plane we want to deconstruct, so that's the x-axis vector of that plane, and this is the one we want to use instead of the world vector here. So instead of that, I'm going to take in amplitude. Yes. So that is the vector, and the amplitude comes from here. We don't need that one. And this is our new vector. So let's see what we have in 3D. Okay, they are diagonally positioned, but they are not diagonally rotated yet. And this is because the plane here is still the XY plane. So we're going to use this one instead. There we are. 4 rectangles. So let's take this, copy it, and this would be the top sections. Top sections. Connect this one here. Okay, now we are ready to loft the 2 tubes. So in order to loft, we want to merge all the sections together in one list. So the bottom section, the middle section, and the top section. Let me check. Just to make sure, let's simplify this. It's working fine, but we don't know what's happening later. So let's simplify this, and we have 2 lists for the 2 tower tubes of 3 sections, which we can then loft. Here they are. And in the loft component, I'm going to right click on options, loft options, and choose the straight loft. So there are the 2 tubes. We can cut those, hide the preview of the ones before, and let's go ahead and union those. Solid union. There we go. Hide this as well. So now we can use this object. We have our geometry, and this is the 3D model of the tower, of the new tower. Good, now we want to create the genome, and the genome will consist of 6 positions, which can take 4 states, 0, 1, 2, or 3. We are going to create the genome in the same way we created the genome for the Sears Tower, but looks a bit easier since we don't have to deal with the middle core. So basically we need 6 items. So let me drop this one here and clean this up. We need 6 items. Not here. We need 6 items in the cross ref. So 1, 2, 3, 4. So now there are 6, and each of the items will start from 0. The step will be 1, and we want 4 states. So here we have 0, 1, 2, and 3. Here are all the options. 4096, 4 to the power of 6 is the way to calculate that. And now this is our genome. Remove this one and pass that to our genome sequencer here. So this will be the text that gets joined, and let's preview what we have here just to make sure that everything is fine. Yeah, we have 4 numbers divided by 6 numbers divided by dashes. So this is our genome. Let's delete that, we don't need it. This is where we pre-filter based on area, but we can't do it now because the area is not so easy to calculate here. So let's drop that. This is where we will keep our selected designs, so let's keep that for later. And then the genome actually should feed to here where we are decrypting, desequencing the genome. Okay, and these are the heights, and they are not heights, they are the positions in that design, so let's call it sections positions. And we want to use them down here in the 3D model instead of these sliders. So first let's get rid of the 3D model for the Sears Tower. This is where we need to feed the geometry. Once we are ready, this geometry will come in there. And the other thing we want to get rid of is, let's still call this an area, but we are going to be calculating the volume. So let's get rid of that as well. Okay, so genomes. Each tower is described with 6 numbers. And in order to get each of them, so that we can plug it in our definition here, I'm going to use the list item and then increase the number of outputs to count all the way to 6, starting from 0. So these are the 6 numbers that describe the tower. And now I can connect these individual section positions into our 3D model here. But before connecting them, which would already start calculating all the 4,000 options, let's quickly just chop a small set of those so that we can test if everything is working, and only then enable the calculation of all the 4,000 options, which will take around 5-6 minutes. So we want to split the genomes that are coming in, split list. So this would be what we are splitting, but they are still into a tree, so let's flatten the input. And let's start with 5 designs. So we're going to take only 5 designs from now on, and that will be connected over here into the filtered genomes. So let's start with this one. Let's actually graph that, so it's a tree. Yeah. And here we are. Now we have only 5 designs, so let's connect them. That would come here, that would come here, this one here, number 4, number 5, and number 6. We don't need the sliders anymore. And let's see what we have at the end. We should have 5 options. We have actually 10. This is because the data structure needs to be changed here. Let's see how the data is structured here. We have a tree which has 10 branches, and each branch has an address consisting of 2 numbers. The left number, the first one, is 0, 1, 2, or 3, and it represents the option, the design option. And the second number is either 0 or 1 and represents which tube it is. So before passing that to the union, we need to partially flatten that tree so the tubes are in one list and not in separate branches. Again, I'm going to use the path mapper. Path mapper coming in here, create null mapping, and we said that we want to get rid of the second part of the branch. So here now comes a tree with 5 branches, and each branch has 2 items, which then get properly unioned into 5 designs. So let's bring that in the group, and these are the designs we want to pass further down to our analysis and display. And then we also want to measure the volume of these designs, not the area, so let's say volume. Here we are. Or let's do it a bit more explicitly. So these are the designs. We want to measure the volume, and we want to put that here. So instead of the area, we're passing in the volume. Okay, so let's hide the preview of all the preparatory work here. So hide the preview of that, so that we can only see, and then also here at the beginning of the 3D model, preview off, so that we can only see the designs. What does our interface tell us? Filter down to 5 designs, out of 5 total, 5 are displayed. So basically everything is displayed. And these are the designs. They are displayed with the genome, with the floor area, which in this case is actually the volume. So let's correct that in our label over here. So instead of floor area, we can do volume. And we have the shadow area, the neighboring shadow. Basically everything else works. And this is because we've made our definition, even though it's quite complex, we've made it modular so that we can change only the inputs here at the beginning. And let's rearrange that. So this was the genome desequencer. This is the genome sequencer. And basically we want to desequence because later on we will be passing genomes as strings once we start selecting designs, and that's why our definition starts here. And this 3D model can move slightly up. That's not still in the group. Let's move that in the group. And this is our 3D model. And that is our area or volume. Okay, so we have the volume. We have the sun system here. The shadows are working without us needing to change anything. This belongs to that group. We don't need this one. Yeah, the shadows are working, and our display interface as well is working. So now that this is done, let's calculate all the possible designs and select a couple of options. I'm going to come here where we have chopped off only 5 designs we want to calculate and set a large number as a threshold. So since there are 4,000, if we chop them at 5,000, basically everything will end up in the A output here. Okay, save the work, connect it, and let's wait for it to calculate. Okay, this took about 10 minutes to calculate. Let's see what we have. If we zoom into our optioneering interface, we can see filtered down to 4,096 designs out of total the same number. Only 5 are displayed. And what's this over here? These are all the center points from the volume. So the volume component, similar to the area component, also creates the centroid. So let's preview off this point cloud here. Okay, so let's do the same as with the previous design and find 5 options that satisfy one or another criteria that we might have as designers on this project. So first I'm going to select the one design with the maximum amount of volume. So here we see still says floor area. Doesn't matter, we know that's the volume. And if you really want to change that, like I do, then we can come in here and say volume. Okay, so let's go to the sliders over here and filter based on area first. So I'm going to increase this number until we are left only with very few options. Let me zoom in here. Let me zoom in here as well. So we are left now with 8 designs. 8 designs that, in terms of overshadowing the neighbors, kind of the same. This one is a bit better, but that's what we have. So basically, one of the solutions is that the 2 tubes are diagonally stepping from each other at the bottom. At the middle, they are next to each other, and at the top, they are also next to each other, which makes sense. So let's take this design, and here we have the same, but the tubes are stepping on the other diagonal. This one looks quite structurally unstable, so we're gonna skip that one. This one is the symmetrical version of it, and this one here, I think we already had that. Yeah, this one is the same as this one. That's because here, let's say tube A is here and tube B is here, and in the other one tube B is having that state, and tube A this one. So basically they are symmetrical, 3 0 3 0 3 0, and this one should be 0 3 0 3 0 3. So they're identical. So let's take this one. The easiest way for me to do that now is actually to bake the label and copy. The label is here. Bake and just copy the genome. There we go, and then let's go to our selected genomes panel, which is here. Delete everything which is from the previous tower and paste what we have. There we go. We need to delete the new line character, so we have only one item, and here in Rhino we can undo the bake. Okay, so this was maximum volume. Let's now select the design that's performing on both the overshadowing metrics. For that purpose I'm going to go back to our sliders, reset that to 0. This way is faster. And then we want to filter based on overshadowing, so cut off the ones that are not performing so well. Let's stop somewhere here. How does that look? I think this is 0 and that's connecting somewhere here, so this is a good design and this is probably another good design. So let's filter a little bit on the overshadowing. Let's get this one first. We'll keep filtering there. So this is the design, how it looks. Basically the tubes are over each other and that's not really good. So let's skip that. Let's revert a little bit here. Here are some more designs and let's go here. How many are left? 16 are left. So let's choose the one with the highest volume. Now we're down to 4. And probably there are 2. And again we have the symmetrical ones. Okay, so basically at the top it's a thin tower, the tubes overlap, at the bottom they're still diagonally from each other, and this is the reversed one. So let's take both of these, bake the label, and come here in Rhino, copy this genome, paste it in our selected ones. And let's take this genome and paste it in the selected ones. Okay, so now we are at 3 designs. Let's take 2 more. Let's go back to our sliders. So let's reset this to 0 and these ones to 1. Okay, let's go for the top performer on the overshadowing of neighbor metric plus volume, maximum volume, minimum shadow over the neighbor, and the second one will be maximum volume, minimum park shadow. So let's reduce this slider first. So now we're down to 64 designs, which all perform well on the overshadowing metric, and let's get the ones with the highest volume from those a little bit more. There we are. So 8 designs, and they're quite the same in terms of metric. In terms of numbers, so let's see what we have here. So they're not that much different from the one we just saved. They're just wider here at the top. So let's display all of them and let's see what we have. Let's go to the grid and make it in 2 rows. 8 are displayed. Okay, so here we are. Which one to save? You know what, I'm not liking any one of these. Let's see if we have better ones. Like I said, this is a moment where we need to think as architects, and these look too similar to the one we already have, and that was performing better. Okay, so I increased the cutoff for the neighbor shadow in search for more designs, 40, and we want to get the maximum area, so here is more. Let's increase that. Here we are. Okay, yeah, I guess that's it. Then we should be taking one of these. Okay, so let's take this one, bake the label. Oh, it's the first one here, so if I copy the data only and just take the first one, that's also a way to go. There we go, and delete everything after that. Okay, so we are down to 1 more design left, and that was the idea. There is to have the one performing the best on the overshadowing of the park and volume. So let's reset our sliders again. This goes to 1, this goes to 0, and let's start cutting off based on the overshadowing of the park. Okay, so now everything is 0, and let's just choose the biggest area from here. Let's see what we have. The biggest volume. I keep forgetting. Okay, so here we are at 8 designs, and they look kind of interesting. I think we already have this one. Yeah, not really. It has a 2 on the 3rd location, so that's interesting. Let's take this one, bake the label, and take this one and paste it in our selected designs, which is all the way here. So there we go, 5 designs. Now we can enable this and pass that to the genomes. Nothing is displayed because we need to reset our sliders first. There we go, 5 designs. Let's set the matrix grid to 1 by 5. And these are the 5 designs we selected. And we can bake them. So this is the geometry and this is the labels. Let's bake them into a new layer. Selected design, so let's rename that to 9 tubes. Let's make a new layer, call it selected 2 tubes design, and make the current, right click and bake. And then while we are in that layer already, let's stop the preview, let's move them 300 meters in. So they're next to each other. There we go, we have 10 designs, 5 of each typology. Each design comes in with 4 metrics on which we evaluated it. We have the genomes, so later on we can go and reconstruct them if we want. And at that point we can start producing a couple of sample floor plans for these tower designs, a couple of elevations, see how they fit in the context of the city, maybe even do a 3D rendering to get an impression of a point of view from the street, or we can discuss it with our colleagues, with our clients, and see that neither of these actually is delivering what we want, and we need to change the typology again and use the generative system to help us select 5 or 10 options for it. That wraps up what I wanted to show you in this video. Basically how to use the optioneering interface to select designs based on one or another metric or based on your design sense, which often can be quite subjective. Sometimes a shape is more interesting than the other. Not everything is driven by the numbers. Thank you for watching, and see you in the next video where we are going to take a look at evolutionary optimizations.